everybody. It's a pleasure to welcome all my guests on the Into the Impossible podcast, but none more so than when you get to interview a friend and a colleague. And today we're really graced by the presence of none other than Professor Abigail Vieregg, Abby as I call her, of the University of Chicago. Abby, how are you doing in Chicago currently?
I'm doing fine in Chicago. We, like everybody else who can, we're staying home these days and trying to get some work done. It's actually kind of a fun time because it means that we get to embark on a few kind of crazier projects with my grad students while we can't get into the lab. So that's kind of fun.
Yeah, today's theme will be nothing if not crazy. I do want to point out that Abby's is a professor, associate professor, right? You're associate professor of physics and astronomy. Do you have a courtesy appointment? Is that the way they say it out there?
No, it's just physics, actually.
Just physics. Okay. A purist. That's phenomenal. And Abby is a recent winner of the Presidential Early Career Award for Scientists and Engineers. Congratulations. That is a storied cohort. And I understand you were very
including yourself.
That's true. I didn't want to bring that up, Abby. Thank you very much.
That's why I get to bring it up.
That's right. Well, in the time reverse sense, you paved the way for people like me. I understand you were heartbroken that you didn't get to meet President Trump. Is that correct?
Completely heartbraken. But I do have his signature on the piece of paper. So.
As I have George W. Bush's signature. But I actually got to meet him, so that was a nice.
That's cool.
A nice aspect of it. Well, today's event. Well, first of all, I should say that I know you for more than 10 years. I've tried unsuccessfully on many occasions to get you to come to San Diego as a postdoc, as a professor. Luckily, if I had to be beaten out by any institution, it's the University of Chicago. And I'm just so glad that we continue to work together. So as I said, it's a great pleasure to talk to all the scientists who come on the show. And lately we've had a lot of theorists on the show. And more than that, it's not enough to just have theorists. We've had theorists that are proposing truly groundbreaking, if true, ideas and notions about new paradigm shifts for the way the universe is organized. And one of those might intersect or might not. I'm speaking about Eric Weinstein's theory of geometric unity, which some have said might predict even the existence of particles that don't fit into the standard model, either have weird spin properties or antiparticles that have unusual properties. But there's a potential relevance to that project that you worked on for your PhD thesis and continue to work on, called ANITA. And ANITA stands for, why don't you tell me, what does ANITA stand for, first of all?
It's the Antarctic Impulsive Transient Antenna. And we borrow the N from Antarctic, like any good acronym. It doesn't quite fit, but it's the Antarctic Impulsive Transient Antenna. Yeah.
So for those of you watching the video, behind us is really the reason that we met, that Abby and I met, and that's the BICEP2 experiment, which is located in Antarctica, at the center of Antarctica, at the South Pole. And BICEP2 brought us together, first of all, back when we began our interactions. But you had been working in Antarctica for many years before that. So can you first tell us a little bit about your experience on ANITA? What was it that you actually did? Where were you? You were working in UCLA, and you were a fellow Californian. Can you tell us more about what it's like to do that work and what your thesis project was all about?
Yeah, so I've been working on ANITA, I guess, for 15 years, which seems kind of crazy when you put it that way. I should have sent some pictures of sort of the fun pictures of like the old times on ANITA, because it's fun to think back to graduate school. But my thesis was the search for neutrinos with ANITA from the second flight. So just to put that in context, ANITA at this point, ANITA is a NASA long duration balloon experiment, and Brian has flipped to a picture of ANITA. It's on the far right is our
Here's
payload.
A close-up of it.
Yeah.
Here's
the close-up of it. Yeah. And then it's a balloon experiment. So you attach a payload like that weighs a few thousand pounds to basically the end of a huge helium balloon. And the balloon doesn't look that big in this picture, actually, because when it's on the ground, it is only inflated that much. But then when you launch it, into the upper atmosphere, it becomes the size of a football stadium. So it's a huge helium balloon capable of lifting many thousand pounds to about 40 kilometers above the Earth. And then, you build whatever instrument you want to, put it on this balloon, and then it circles around Antarctica. And most people use this platform to look up at the sky, to look for various kinds of radiation that you can't see from the ground because the atmosphere gets in the way. But what we do is we use this platform to get really high above Antarctica to actually look down at the ice for neutrinos interacting in the ice that then give off a radio signal that we look for in the balloon with the payload. And we do this because we want to see a huge volume of ice all at once, because the particles are so rare that you need to monitor a very large volume to have any prayer of seeing anything. So at this point, ANITA has had 4 flights. I was a graduate student on the 2nd flight of ANITA. That was my first trip to Antarctica in 2008. My thesis result was the main result from that experiment. Since then, of course, I've worked on the 3rd and 4th flight of ANITA as well. And I also was on the 1st flight. I was just a junior graduate student though, so it wasn't my thesis. Yeah, we are still doing analysis of the data from later flights. My group, I have a postdoc and a student who are still, partly working on this, the data from this experiment.
When is there an upcoming flight that's planned?
So there's no upcoming flight of ANITA that's planned, but we did propose an experiment that would be sort of the follow-on to ANITA. And basically what's happened in the last 5 or so years is we've had a little bit of a technology breakthrough that has allowed us to build a much more sensitive instrument. So we think we can design an instrument that's about a factor of 10 more sensitive than ANITA. So we've proposed that. And it's called PUEO, which is a funny name for an experiment. The reason we picked that name is because the University of Hawaii has always been a major part of this project, and PUEO is the name of a Hawaiian bird, a native Hawaiian bird. And it also fits the acronym well.
Okay, I'll be interested to see that replace the penguin as the official bird of Antarctica.
And that's right. That's right.
That would be probably cruel to bring it to Antarctica from Hawaii.
Yeah, we wouldn't do that.
So our listeners are probably familiar with exotic phenomena. We've had on Barry Barish from LIGO talking about interesting phenomena in the gravitational wave sector. And we've had on many people talking about the cosmic microwave background and the looking for signatures of new physics or old physics in the cosmic microwave background and the ancient photon sector. Neutrinos are different. What exactly is a neutrino? What's a proper way to think about neutrinos? And are all neutrinos, equally good to reveal new physics the way that all photons are? I would say photons are like commodities. You've seen one, you've seen them all. Are neutrinos of the different types, are they equally good at possibly revealing new physics that you might hope to expect to see?
Yeah, so first, I guess there were a few questions in there, but the first I'll answer is, what is a neutrino, I guess? There's many ways to think about a neutrino. I mean, at its basic definition, a neutrino is a fundamental particle, which means that it can't be broken down into smaller pieces, just like an electron or a photon. It's something that we think is sort of like a basic building block of matter. A neutrino is a cousin to an electron. It's in the same family of particles. It has similar interactions as an electron, which is just like an electron is, the electrons are everywhere. They're particles that are in atoms, right? But a neutrino,
you never trust them because they make up everything.
Right, that's right. But a neutrino doesn't have charge. So the thing that's weird is if you imagine an electron and then you have an electron with no charge, the way an electron interacts with everything is it interacts electromagnetically. It interacts because it has charge, like it's, attracted to other stuff. But a neutrino, it's like the weird cousin of an electron that doesn't have charge. And so then you're like, well, what the heck? How is it going to interact with it? How do we know it exists, right? To know something exists, it has to interact with something for you to see it. So it turns out that there's another sort of fundamental force called the weak force that is aptly named because it is much weaker than the other forces. And that's how neutrinos interact. So they don't interact very often. And that's why people call them, people use the flashy word like a ghost particle, right? Which is kind of a funny word, but why do they use that? They use it because they kind of move through the universe, not interacting very often. It's hard to see them.
Mm. And there are multiple.
Are all new,
Oh, go ahead.
yeah,
Sorry, go
go
ahead.
ahead. No, I was going to say, so your other major question was like, are all neutrinos the same for discovery? So there's different kinds of neutrinos. They just, we think there's, in the fundamental standard model of particle physics, we think there's three kinds of neutrinos. For some reason, things seem to come in threes in particle physics, and we don't really know why that is. But in any case, there seem to be three, types of neutrinos. For us, they're all basically the same in terms of their ability to lead to discovery. Because what we're trying to do is use neutrinos as messenger particles to learn about astrophysics. So we want to learn about what is the physics that's driving the most, the most energetic things in the universe. What is accelerating the most energetic particles in the universe? How do those engines work, and what are those sources? What do they look like? So for us, all neutrinos are the same for helping us learn about that.
And so ANITA was designed specifically to look for one of the three flavors, as I understand it, the tau neutrino. Is that correct?
So actually, ANITA was designed, so ANITA's a little bit of a complicated story. So ANITA was designed actually to look for all three flavors of neutrinos. The main way that ANITA looks for neutrinos is a neutrino comes from somewhere in outer space, some very energetic source in the universe. Maybe it's an active galactic nucleus, which is a black hole in the center of a galaxy that's accreting matter. Maybe that process makes high energy particles. That's a common theory. Okay, so let's say a neutrino comes from there, comes to the Earth, and it hits the Antarctic ice and makes a shower of particles. So a neutrino, it's like billiard balls. A neutrino comes in, hits a nucleus in an atom, and then it makes like a splash of stuff. And that's a bunch of particles. That splash of stuff gives off radiation. That's what we look for. And any flavor of neutrino can do that. And they make pretty similar showers as far as our ability to detect them, goes. If you could really detect the fine details, you could tell that the showers would be slightly different. But as far as we care, they all kind of look the same. So that's ANITA's main method of discovering neutrinos. Turns out there's another channel for ANITA that is only sensitive to one flavor. That's the tau neutrino. So it's like we have two ways of looking. One is through this channel that looks for all the different kinds of neutrinos. And then another way of looking is this channel that's only good for looking at tau neutrinos. And the mechanism is slightly different for that.
I see. Now, I want to get back to why that particular channel is so pertinent, perhaps, or not, to these tantalizing, provocative new conjectures that we've heard about. But first, I want to talk a little bit about our shared fondness for Antarctica and why you would go there instead of staying in Chicago. This is a live view out your window of the University of Chicago's Lake Michigan oceanfront. Or it's probably Hawaii. But why go to the trouble of going down, to the bottom of the world, literally, great expense and so forth? Why go to that great lengths, literally, to look for this humble, ghostly particle?
Yeah. So for us, it's like, I think it's like kismet. It's like a coincidence of many factors that make ANITA possible. One is that the long duration balloon program exists in Antarctica. Like NASA flies payloads over Antarctica. And why do they do it in Antarctica? So this is independent of ANITA. So why does NASA fly these big payloads over Antarctica when they could launch them anywhere? The reason is because in Antarctica in the summer, these winds called the circumpolar winds. So in the upper atmosphere, these winds set up that mean that when you launch a balloon, it just gets swept away in a circle around the pole, and it allows you to just keep rotating around Antarctica. And then eventually when you get back to where you came from, you can cut your payload down and recover it near where you started. And that's unique in the world. Like I guess you could do that in the northern hemisphere, but it's difficult to do that because there's not land everywhere near the pole in the northern hemisphere. So that's why the balloon program exists in Antarctica in the first place, is because if you want to launch a big payload on a balloon and do any science with it and have it up for 30 or 40 days, that's a good place to do it. in other places in the world, you'd have to cut the payload down after a day or two because it would drift too far away. So then ANITA is a funny thing because it takes advantage of that, but it also takes advantage of the fact that that's happening over, you know, an ice sheet that's a few kilometers thick. And what we use as that's two things that like work together in favor. The balloon program, the winds in Antarctica work in our favor, and then the thick ice sheet. And then the third thing that really works in our favor is that Antarctica is also a very quiet place to work. There's not a lot of noise. So when you launch your very sensitive detector, you actually have a chance to see physics rather than just like man-made radio interference all the time.
And so would it be fair to say that IceCube is a similar experiment, or is it more of a competitor? Or are they sensitive to similar effects, such as the one that prompted this discussion?
Yeah, so IceCube is a little bit different of an experiment. It's a complementary experiment where IceCube looks at a little bit lower energy neutrinos and we look for a little bit higher energy neutrinos. And there actually isn't that much overlap between the two techniques. And you can think about it this way. So ANITA is really high above the ice and it looks at a lot of ice that's pretty far away from the payload. Whereas IceCube is a detector at the South Pole that has a bunch of detectors right in the ice. And so what they're doing is looking at a smaller piece of ice, but they're looking at it much more close up. And so that just allows you to see smaller signals. It allows you to see you know, smaller particle showers, which means you can see lower energy neutrinos. So IceCube is really geared for a little bit lower energy, and ANITA is really geared for the highest energies. There is some overlap, but it's pretty complementary, really.
Having been to both environments, both the South Pole and the coast of Antarctica, McMurdo, where these balloons are launched from. So can you talk a little bit about what it's like to get there? I showed the plane, the the C-17 that takes you down. If you're lucky, sometimes you get a C-130 and that's not so lucky.
Right.
Can you talk a little bit about what it's like to be there in graduate student days and then come back as a professor or, you know, senior leader in the field? What's it like at these two different environments? I didn't see too many people with purple, you know, leisure suits and blue hair at the South Pole. It seems a lot more business focused, serious at the pole. But how do you compare the two different sites for those of our audience who haven't been there?
Yeah, so I've been obviously to both McMurdo Station, which is on the coast of Antarctica, and South Pole. So McMurdo Station is where the balloons launch from. It's you know, it's warmer there. So in the summer, it's actually pretty bright and sunny all day. And it's, you know, 20 degrees Fahrenheit. And so it's actually kind of nice. As you can see, this is a picture of New Year's Eve. That's midnight on New Year's Eve. And, you know, we're all outside having a good time. And you can see it's not actually that cold out on January 1st, which is the height of summer. Of course, if you were outside at the height of summer at South Pole, it would still be minus 20 or something like that. And that would be pretty cold to be doing something like this. You know, life in Antarctica is, it's pretty fun. I think sometimes I think about it, it's kind of like college, like you're in a dorm, you've got shared cafeteria, you see the same people over and over. Oh, sorry, Brian, I can't hear you.
Oh, sorry. If you go to like a college inside of a strip mine, you know, it's also very industrial at McMurdo. But yeah, I like it better than the South Pole. I don't know why people like the South Pole, but
McMurdo's kind of fun. There's about 1,000 people there. Most of the people there are not scientists. Most of the people there are really hardworking people who are making science happen by supporting the station and supporting the scientists to do, you know, to get the science done. And yeah, I don't know, life in Antarctica is pretty fun. I will say, you know, something Brian said made me remember, you know, life in Antarctica as a graduate student is very different than life now in Antarctica. Now, like when I was a graduate student, that's a picture of the cafeteria on Thanksgiving. You can see someone's wearing a tie.
Yeah.
That's like, you know, that's Thanksgiving in the cafeteria. But life as a graduate student in Antarctica was like pretty carefree in the sense that you could turn off everything else in the outside world and pretend you had no internet, even though you really do have internet. and just you can just be with your experiment. Like you can just wake up every morning, someone cooks breakfast for you, then you go to work all day and someone cooks lunch for you, and then you go home and you don't have to worry about like paying bills or commuting, or it just is. You're just working on your work. And that was great. It really.
Now, I mean,
Now,
yeah. Would you pay for that? Right? How much would you pay for that? You could bring your daughter there, right?
Right. It's funny, but now as a professor, when I've been to South Pole in the last few years, it's very different because like you still have this whole other job that you have to do at home, and you spend all day doing that same thing, working on your experiment. But then the switch flips, and at night, then you have to do your other job that's still at home. So it's much more stressful to be in Antarctica now.
Yeah, I can imagine. Oh, thanks for that. That's a very interesting insight into the difference between these different phases. And most of the general public, if they know a scientist at all or know somebody who's in physics, would just know what we do from the Big Bang Theory. And it's a fun show. And actually, your former advisor, as a graduate student, had some involvement with that show, right?
Yeah, my PhD advisor is David Salzberg, and he's the scientific consultant for the Big Bang Theory. And then I think he's also doing Young Sheldon, the sort of follow-on show.
I see. Okay. Yeah. So, I mean, that's obviously there's a lot of artistic license that takes place there, but it is very different. You don't really see both the really good aspects, as Abby just mentioned, as you mentioned, but also, the challenges and different levels of being a scientist. And really the stakes rise and continue to rise as you're doing more and more research and getting to different heights, literally in the case of ANITA. So getting back to the reason for our conversation today was this very provocative report, which I first saw in the most august of all scientific journals called the New York Post. And I pointed out that, what they say about Nature magazine could probably apply for the New York Post, that not everything, just because it's published in the New York Post doesn't necessarily mean it's wrong. But they have some pretty outlandish statements in there, and even included some from the principal investigator on this project, Peter Gorham. And I wonder, first, can you take us through what is a principal investigator? Is that a principal, from high school who, turns into a private investigator? What exactly is a PI? You are a PI now. So tell us, what are you? What is a PI, first of all?
Okay. Yeah. So in PI is used in a variety of different ways, but in this way, it means that Peter is the sort of head of the project. He's like, there's 7 or 8 institutions, each with faculty working on this project, and Peter is the one who ultimately is the gateway to talk to NASA about the project, right? Like, so he's the one who is sort of ultimately in charge to make sure that the mission succeeds and we do our science and all of that. So the PI responsibility is a little bit more than the other faculty, I'll say, especially in NASA. NASA is a little bit of a, right, I mean, different government agencies put a little more or less weight on the PI status, but so that's, I guess, what a PI is. It's sort of the professors working on the project, he's the professor who is the lead, the one that people would talk to, and the one who is ultimately sort of the connection with NASA.
So what he's quoted as saying in this article and others really revolves around the behavior of these poltergeist particles called neutrinos, which I always like to point out, they're really the only form of dark matter that we know exists. I mean, they have mass and they weakly interact. They don't interact with photons. And yet they do have an ability to exhibit some sort of bizarre behavior when they pass through matter. We won't get into the exact effect that you're searching for. It's very technical. We'll have some links to that. But they, kind of headline that's printed, at least in things like the New York Post and others, is that because of the way that these particles interact so inefficiently, these tau neutrinos, that the only way they could be detected is if the neutrino changed into a different type of particle before passing through the Earth and back again. And he's quoted as saying that there's this phenomenon that could explain this, and that somehow, and we don't exactly understand even as experts in the field, how this implies the existence of a parallel universe, let alone the multiverse. But can you say something about how the tau neutrinos, assuming that that this effect is borne out and is verifiable, which you can also comment on? I mean, your confidence in this result, not the interpretation, but how confident are you in, say, the data themselves, and what other sorts of phenomena could explain the results but not be so sensationalized?
Yeah, so I think there's a lot wrapped up here. So I'm an experimentalist, which and so I'll answer the question about the data first, which is, I can tell you what we saw. So ANITA was designed to look for high energy neutrinos, and what that really means is ANITA is an extremely sensitive radio detector that looks for little blips of radio waves. And when we think we see something interesting, we record it and we look at the data later and analyze the data. Okay, so there's other things that could make radio blips other than neutrinos, and that's called background. So this is common in like particle physics experiments. You see some number of events, interesting time frames in our case, and you're trying to like sift through those interesting time frames to see if there's any neutrinos in there or any other interesting physics. And you're trying to sift through what other, there may be other things that kind of mimic that signal that would be really boring. So one example is, in our case for ANITA, is man-made backgrounds, meaning like people at McMurdo Station, right? You turn on your snowmobile and it makes a radio blip. So that's a, problem for us. We can try to measure that, and there's lots of ways to sort of characterize the signals that we think we can basically distinguish the signal from a neutrino from other things, but it's not a perfect discriminator. You can never build a perfect discriminator. So what this means is that at the end of the day, you're left with some background, we call it. You're left with some, estimate of what sort of the noise might be left in your analysis. So we did an analysis looking for showers made by both cosmic rays, which are protons mostly, that make showers in the atmosphere, and ANITA sees a bunch of those cosmic rays. It's not like an exciting new discovery, but we do see cosmic rays because they're coming at us all the time. And another type of particle that might make a shower like that is a tau neutrino. But the difference would be that a cosmic ray, of course, is coming from above, and it would make a shower. And then the radio waves from that shower actually, for ANITA, actually reflect off of the ice and then come back up to ANITA. So it's kind of a funny geometry problem where ANITA is so high above the atmosphere that we actually don't see cosmic rays above us. We see the reflected radio waves off of the ice. It's like the ice is a mirror, and the radio waves come back up. We also could see a tau neutrino, which could come through the Earth, interact in the ice, make another particle called a tau lepton, which is a charged particle that then makes a similar signal. So basically a tau neutrino could ultimately make a very similar signal to a cosmic ray air shower, except for the fact that that shower is coming up through the Earth. And because it's coming up through the Earth, the radio waves don't have to reflect off the ice to get back to us. So the signal, the thing that's kind of subtle is that we see a bunch of cosmic rays with a signal that we can, we've seen like tens of them. They all look very similar. And then we see these few events, there's 2 events that look very much like a cosmic ray, except they're flipped upside down. So you ask, like, how did they get flipped upside down in the data? Well, they got flipped upside down because the cosmic rays reflected off the mirror. And when they reflected off the mirror, they got flipped. But these upgoing tau neutrinos, those signals didn't get flipped. So it's like, that's how ultimately we're doing the distinguishing between this sort of what I would argue is relatively boring cosmic rays, although some people really think those are interesting, and this much more interesting neutrino signal. It's a subtle thing where, like, it's just because of the way the geometry all works, one of the cosmic ray events should look flipped compared to the neutrinos. So we saw 2 events that had the opposite flipping from all the cosmic rays that we saw. And the question is, like, how does that happen? How does it, is it you see two events like that, and you ask yourself, like, well, the first question an experimentalist asks, what's the first question an experimentalist asks, Brian?
What else could
Is it
explain the
background?
signal?
Yeah. What else can explain it? Like,
what did I do wrong?
Yeah.
How did I mess up?
Yeah, what's wrong with my experiment? So the first question you ask yourself is like, what's wrong? And so, and the different ways to phrase that is, what are the other backgrounds? So the other backgrounds are some man-made noise. Well, we try hard to characterize that, and we think we have like a good estimate. And this is still, 3 or 4 sigma above that. And then the other background could be that maybe there's some weird thing with the ice where, like, when you reflect these cosmic ray signals, maybe they don't actually flip for some reason. Maybe there's some weird interference happening at the surface that makes it sort of look as if it, didn't flip. And that would be a background. So that some of these backgrounds are really hard to estimate, as you can imagine. It's really hard to like make a good guess as to what those backgrounds are. But we've done quite a bit of simulation, and we think it's hard to explain these events with backgrounds like that. So there's 2 events left, and then you're an experimentalist and you've got this data, and you do what you think is your due diligence on what else could it be background wise, and then you publish the data. So then you say, like, well, this is what we saw. We saw 2 events on a relatively small background, and we don't know what they are. Okay, so that's fine. I think that's the way science works. Like, you can't sit on your data forever just because you don't like the answer, right? Just because you wish it would go away. And I've seen that before.
Yeah.
You can't do that. So at the end of the day, you say, like, all right, well, we'll publish our data, and we won't say anything outlandish about it. We'll just say that we don't know what it is. So then the story continues, right? So then the first sort of set of so then what happens in science after that? An experiment puts out this result that says, we saw 2 of these events that look like high energy particles that came through the Earth. We don't really know what they are. And we don't know if it's real or not, but here's our background estimate, and it looks hard to explain. Okay. So then a set of theorists come along, and the first set of theorists points out what is frankly pretty obvious, and that's that the way that the distribution of what these 2 events looks like is actually pretty inconsistent with neutrinos, which is kind of a weird thing. Like, they come through like the whole Earth. They're really steeply up going to ANITA. And neutrinos, even though they're these ghost particles that we think they don't interact very often, at these really high energies, they actually should get absorbed in the Earth. So to have something that comes so steeply up going through the Earth without also seeing a bunch of stuff coming really shallow is very unlikely for a regular standard model neutrino. So that's sort of the first set of papers that came out after we published our data. And like,
and we should stop and say that the data were published in 2018 or
2016. 2016 might have been the first paper, and then there was a second paper in 2018.
Right. Okay. Yeah. Keep going.
Yeah. So the first set of theorists came out and said an important statement, which is, these don't really look like tau neutrinos. We kind of already knew that, but I feel like our job as experimentalists is to stay true to the data and try not to push the hype, right? Because if we as an experiment came out and said, hey, this is, whatever, 4 something sigma above background, and it doesn't look like a tau neutrino, then all of a sudden you've upped the hype, right? Because then the following question is, well, what is it, right? And this sparked actually a fair number of groups to say, like, oh, let me try out my somewhat more crazy to somewhat less crazy theory ideas on a fun side project. I think a lot of people did this. There were a bunch of theory papers about supersymmetric particles called STAUs. Maybe it could be some supersymmetric particle. Maybe it could be some dark matter particle. Maybe it could be, whatever. There's a variety, sterile neutrinos. Like, there's a variety of, more or less out there ideas of what it could be. And that comes from sort of independent theory groups over the last few years.
Yeah.
Okay. So then that, like, makes people within the field are kind of having fun, I would say, and saying, like, oh, wouldn't it be great if this was real? But I mean, it's 2 events. and the experimentalists aren't jumping up and down about it. So that probably means we shouldn't jump up and down about it, but we're still going to write our theory papers because that's fun. And then the news gets a hold of it.
Yes. And that cycle I want to get into in a bit, but you know, they'll take one quote and then it seems to have gone a life of its own. And these papers don't come with Surgeon General warnings that they, you know, I always find it, and I wonder, you know, if you had a similar experience back in the BICEP2 days when we together, both our 50 colleagues on BICEP2 experiment published a claim detection of inflationary gravitational waves. Even the week before we published, I was getting emails from former professors and colleagues, all theorists, that were saying, you know, we heard this rumor, and I don't know how that got out because I know you didn't say anything. I know I didn't say anything, but they were asking us for, you know, could it explain, you know, this magnetic monopole, whatever. It could it explain string gap? You know, my theory is is completely in concert with this, and I wonder, you know, do you have this impression? I often feel like theorists, because theory in some ways comes down to two different flavors as I often see it. It's either incremental, but not in a bad way. It's just adding to the standard model and understanding different extensions of it. Or it's truly serendipitous in that you really conjecture, oh, there's this new Bose-Einstein condensate that could occur, or, you know, or what have you. And the same is true in experiment. There's incremental improvement that we make. We build better CMB detectors, better muon detectors, and neutrino detectors, and it gets steadily better. And then sometimes you hear a beeping radio noise from outer space, and lo and behold, you discovered pulsars. And so I wonder, is there a parallel in your mind between those two? And why does the hype, if you do believe it, it seems like this hype, as you said it, you know, kind of gets amplified despite the efforts of the experimentalists. Why do you think that is? I have some ideas, but I'd like to hear, why do you think the hype comes from the theory side in a certain sense? You know, the claim that, yes, we're living in a multiverse, and not only a multiverse, but time goes backwards. And why does that happen so often, in your opinion?
Yeah, I mean, it's interesting you bring up BICEP2, and I think these stories are actually a little bit different. So in this case, the experimentalists, we published our data, but with no pomp and circumstance, right? It was like, you know, here's a PRD, which doesn't mean much to the audience, but like, here's a paper doesn't even rise to the level of like a fancy journal. It's just like an okay journal. We're going to put it in, right? Because we didn't think it was, you know, that flashy. Right. And we didn't put out a press release. And yes, we talk about it at conferences, but it's like, you know, here are these two events, here's the background. And then we just leave it at that. Like, we don't know what it is. Here's what a few theorists have interpreted. Isn't that great? Right. But I think in this case, some of the hype has been driven a little bit by theorists, but I don't think that they've been intending to drive hype. I think that's just partly the role of theory. I think partly the role of theory is to look at what could be an interesting result and come up with ways to explain it, right? And so that's what the people who wrote this paper about the thing that ultimately led to parallel universes with the time running backwards, the person who wrote it, Louis Sankardoki, is a very well-respected theorist, and he's just, you know, writing something fun, you know, something interesting down for the scientific community about what it is, right? And he wrote that paper last year. I mean, it's not like it happened this spring, right? And so then a science news outlet called New Scientist wrote actually a pretty good article about his theory paper as well as a few other theory papers, and interviewed the PI of ANITA, Peter Thiel. And, you know, it was a pretty even-handed, I think, coverage of the sort of interesting thing. Like, hey, they've got these events. We don't really know what they are. It could be background, but here's some interesting theories. And then the New York Post and others just picked the headline up, right? And all of a sudden it's NASA scientists claim they've which NASA scientists never claimed this, right? Of parallel universe with time running backwards. So I do think that it's partly the role of theorists to look at experimental results and try to do some interpretation. Mm-hmm. I think that this story for ANITA is a bit different than BICEP2. BICEP2, and I can say this as someone who was on the experiment, was a little more driven by the experimentalists, right? It was, hey, we built this experiment to measure gravitational waves from inflation, and at least the press release said we think we did it. The scientific paper was much more even-handed about what the results were. They just said, we saw an excess signal, which is true. We saw an excess signal, but the press release definitely said,
first direct evidence.
First direct evidence. And that particular result was the pomp and circumstance around that result was driven by the experimentalists, for sure. So that's a little bit of a different situation.
Yeah, as you may know, I know you've read the book that I wrote about this, that I view serendipity as sort of an interesting, maybe an assayer, type substance that can really separate out science that is perhaps more subject to confirmation bias, the peril of looking for something. I always get asked, well, what did you hope to discover? And, those are phrases that we, of course, think about. I mean, we wouldn't be human beings if we didn't think about it. And contrary to stereotypes, we are human beings. I can attest to Abby's humanity and graciousness. But the fact is that, headlines, usually are driven by, kind of serendipitous discoveries in the sense that you really weren't expecting. And yet it's almost the opposite. Like, the public will pay more attention to something serendipitous if it has an interesting explanation, which may or not be blessed by the authors of the data themselves. So just to close up, I want to talk about, your philosophy of science, and that, you mentioned that it's not, you are building a successor to that experiment in a sense, but the question of how and when to turn off an experiment has always been interesting to me. In other words, BICEP or Simon's Observatory or Simon's Array, we could observe for many years and not see anything, quote unquote, and that we wouldn't have seen the evidence for the thing that we were seeking. Similarly, the Higgs boson detection has been claimed as the main output of LHC, but it's not been turned off yet. And people are trying to speculate on what it would take to build a bigger, better experiment. What do you think is really, kind of the ultimate point as a leader in the field? How do you feel you come to a decision? Let's terminate this experiment. Let's look to design another one, because you've created new experiments and new ideas. How does that work? Is that a creative activity? So two-part question. How do you know when to shut off an experiment, pull the plug, to use a crude analogy? And two, how do you think of these ideas for new techniques and your approach as an experimentalist?
Yeah, so I think the question of when to shut off an experiment is really hard, as you just said. Like, it's really hard. I think, to me, that's where I always try to retreat to the science questions, right? Because that's what we're ultimately doing. We're ultimately trying to answer science questions. So I do think it has to be driven by the science. And what I mean by that is, I think there's at least two kinds of science, but there's two kinds of science. One is where you're kind of looking for a particular signature of a theory that someone or multiple people have written down in multiple ways. Like, it's kind of like looking for something that you know what you're looking for, because a bunch of theorists think it's interesting to go there, and that's where you go. And I think that's when it's important to have good theory colleagues, is like, there's people whose job it is, and that they spend their lives helping experimentalists try to figure out where to go next, right? Mm-hmm. So one could argue that you shouldn't build or run an experiment if a bunch of people agree that there's nothing to see there, right? Like, if you get a factor of 2 more data, is there nothing to see there? And if, all your theory colleagues that you trust are telling you have to think hard about making the decision to go forward anyway, right? I mean, or try to go forward. But the other kind of science, I think, there is a little bit of this, like, unknown, right? Sometimes you just stumble across, it's serendipitous. You stumble across something that, like, no one thought would be there. So I don't ever want to become someone who only looks where people tell me to look, because I think in some ways, like, the great discoveries will also be made by looking in places that, that people think are crazy, right? It's on some level, there's kind of, on some level, if you only ever looked where people told you to look, what fun would that be? Yeah. So, right. So if you have an experiment that's running, like ANITA has had 4 flights, and we can ask the question, should we fly a 5th flight of ANITA? And I actually think the answer to that is probably not, with the same instrument. And that's because, the first flight is a bit, when ANITA 1 flew, it was kind of groundbreaking, right? There was nobody else who had designed any experiment like that who could look at the highest energy neutrinos. It was just like this open field. For all we knew, there was, super heavy dark matter decaying and giving us tons of neutrinos there. And like, we could have made a great discovery with ANITA 1. But a lot of those models, have been ruled out.
It's like a victim of its own success, right? Yeah, it's
and then
cannibalized its own.
Exactly. So ANITA 2 is a little better, ANITA 3 is a little better, and you combine, and eventually you sort of say like, well, is another 50% worth it or something? And eventually you kind of like, maybe it's because I'm used to looking at plots on a log scale where like, where I always think in factors of 10 rather than in adding. I always think like, can I get a factor of whatever rather than can I add a little bit of sensitivity? And at some point you have to sit back and redesign your experiment. So that's the question, I think, about when to turn it off. And partly that has to be guided by theorists, I think, of when do you say like enough is enough? If there's no interesting model right below where you are, why would you keep running? The question of technology development is another one that you asked.
Yeah. How do you create these ideas? Is it like an art? Is it just inspiration strikes you? How does your mind work?
That's the part that I like to do, and it seems like it usually comes in the middle of the night for me. Like it's at some random time of the day, I'll be walking outside. Like basically, I spent the first. I guess I've been a professor for 7 years or something, and I spent the first 5 or 6 of those years developing more or less one idea. So it was one idea to build better technology for experiments like ANITA and experiments that are sort of the ground-based version of ANITA that we're actually sending to Greenland this summer, fingers crossed. In a few months, a bunch of hardware should leave the front door of our lab. But I basically spent the first 6 years developing one technology advancement. And that's because it was a good one. And, you go through like 10 ideas or 100 ideas that are only okay or frankly bad. And then you come up with like one good idea. And it turns out that, and if it's feasible and it works, then it can change the field. And, it's not like it's going to be some major revolution that's going to totally, change our understanding of the universe, but at least not right away. But it is, this new sort of electronic system will get us a factor of 10 improvement on ANITA. And it will, I hope and think it's probably going to be the case that it'll be the sort of heart of the next generation of ice cube, actually. So yeah, you start with the technology advancement and then see what happens a few years down the road once you run it.
So it's fascinating when I think about the fact that you have been involved in 2 different projects, which independently, not through your own doing, have claimed at one point or another, or been led to the claim that we live in a multiverse. First with BICEP2, of course, discovering what we thought was direct evidence for inflation, which has as a concomitant companion the existence of the multiverse in many people's estimations. And now with ANITA, so I think you're the only person in that Venn diagram who sits at the intersection. So I want to ask you a question that I ask all my guests, and that's, if you could go back in time, what sorts of events would you, or what sorts of advice would you give to the younger version of Abby? And the reason I do this is the name of our podcast is the Arthur C. Clarke Center for Human Imaginations Into the Impossible podcast. And I don't know if you're an Arthur C. Clarke fan, but he had many laws. His first law that you probably have heard is any sufficiently advanced technology is indistinguishable from magic. You might have heard that. But his second law is the only way to find out what is possible is to venture beyond a bit and go into the impossible. So I want you to talk to the 20-year-old Abby, before the arc of your life took its shape that it has now. What things seemed impossible to you back then that now, by virtue of your going into the impossible, now make perfect sense?
Well, I think it's actually scientifically, it's an easy question to answer. That when I started graduate school on ANITA, um, astrophysical neutrinos hadn't been discovered yet. So no one had seen a neutrino from anywhere in the universe except from the sun or, well, supernova 1987A, but from any other source, like no one had seen anything.
Mm-hmm.
And that happened for the first time in 2013. And the other thing that has happened since I started graduate school is the discovery of gravitational waves. So in this particular field where we're looking for high energy phenomena in the universe and trying to characterize what is happening inside of high energy sources, when I started in the field, there was no field. Like there was no multi-messenger astronomy. Like it wasn't a thing because there was no multi-messenger. There was no there were no neutrinos that had been discovered. There were no gravitational waves. And now it's like, I really think in the next 10 years, it's just going to accelerate and more is going to be possible. So that's kind of an easy question scientifically of like, I did not, when I entered the field, it really was very different than it is now in terms of what is possible to do. And that is in large part due to major breakthroughs from very large experiments, right? Like LIGO and IceCube, both very large experiments.
Yeah.
I think personally, like on the, what do you, I actually do a lot, as you know, Brian, because you're faculty also, you do a lot of talking to the younger version of yourself, don't you?
Yeah.
Like when you talk to your students, yeah. I mean, not all of them are the younger version of you, but a lot of the times when I talk to my students, I'm telling them things that I wish I had heard.
Yeah. It makes me think about being a parent, because exactly the same way as I'm sure you've experienced, you'll say things to your daughter, or they'll say things. Yeah.
Right. But I think, what I would probably tell my 20-year-old self is I spent too much time worrying about what other people thought. And I think that's just in general, that's probably human nature. But like, in graduate school and in early days of scientific, development, what you want to do is develop your technical expertise first, I think. And also at the same time, like keep in mind the creativity, because you're going to need that leader. Like once you're faculty, you're going to need to be able to dream up all these experiments and go do them. But I think early on, I spent too long trying to sort of please other people and in like my mentors and stuff. And if I just sort of gone off and like did my own thing and just, I think it would have been a faster sort of or more rewarding path through. I definitely do that much more now. I just like do, the things that I find interesting.
Yeah, I think that's really great advice. Looking at things, and one of our one of my the favorite podcasters is a guy named James Altucher, and he speaks about this as kind of choosing yourself, where you really can decide for yourself to be your own mentor, or you could be your own. You can live to impress yourself. In other words, we spend so much time as academics, and I'm going to go on his show in a few weeks, and one of the things I'm going to talk to him about is, well, academia, you really can't choose yourself. Like it's not possible. Well, you can really have a side hustle. Let me just design this $100 billion experiment in my side. It's not the same as starting a gourmet soap company. I don't know what people do for side hustles, but the point is, it's harder in academia. You can't choose yourself to go to grad school. You can't choose yourself to go to college. You can't choose yourself to get a postdoc. You can't choose a grant to get. You can't choose a faculty job. It's like all these things, and all along the way are these gatekeepers. And no matter how high you get, and and you're still, we still experience it, you and I, as tenured faculty, right? So existing, as you say, with the comfort of that milieu, but knowing, as you have developed a brand. Like I look at you and I see you have a brand that I associate with Abby, and there might be some brand, tarnished as it is, that people associate with me or something, but that's what I remember meeting you for the first time, and you really kind of brought that up in terms of, the graduate student brand is to do something that the other people can't do on the project, and to play that essential role and remain essential. And I see that you continue that, and your students are lucky to learn from a mentor like you. So I want to thank you very much for journeying into the impossible with me today. And I know you're very busy at home and at work, and taking the time out of quarantine. And I hope that we're together under future circumstances that allow us to be actually in person. So before we go,
I know.
Can you tell people where to find you on the web? I'm going to post a link to your blog, not because it's, super up to date, as you know, but because it gives an insight into what it really feels like to be an experimental scientist, as Abby is, working at the frontiers of human knowledge. And besides the blog, which I'll post, and your website, is there anything else that you would like the audience to know about, or where to get in touch with you or find you?
I mean, I think my website has contact information for me, but you can always write me. My UChicago email is the best way.
Okay, great.
So,
well, Abby Vieregg, professor, University of Chicago, Department of Physics only. It's a pleasure to see you. It's always fun to have a conversation with you. I feel like this is like a virtual beer that we get to share.
Thanks, Brian.
It's a little early.
I was thinking about it, and the last plane I got on was actually to go to San Diego in like October, and I saw you.
That's right.
That's the last time I've traveled.
Oh wow!
Because I know, because I had a baby, and then this hit. So there you go. I haven't traveled since then.
I know. In some ways, it's good, but anyway, we won't tell our bosses about that. Right. Abby, thank you so much. Have a wonderful day.
Okay. Thanks, Brian.